Right, so there you go. Title of the talk, beautiful beach. Love Malaga, first time here. You got great people, great food, it's all good. So let's get started. So that's what I'm going to talk to you about today. So why should I care? What can we do with IBM Java and GPUs? It's all free. This is a complete technology pitch. Okay, not trying to sell you a single thing. High-level overview of GPUs. So there's a picture of some dung beetles here and a picture of some ants moving leaves. I want to compare CPUs to GPUs. So typically with a CPU, you might have only a few threads available, but these are quite powerful threads. They can do a lot of things. They can handle complicated code quite easily. Now with GPUs, on the other hand, you might have a lot more threads. So maybe you can fire off, a few thousand, a few million threads at once, but these threads aren't so clever, if you like. So they're going to operate on each section of data independently, and they don't really deal with complicated code that well. So my analogy here is, GPU on the left, loads and loads and loads of threads, but they're pretty dumb, these threads. They can't really do much. CPUs, you've got your big dung beetles moving, the big ball of dung. And traditionally, we're going to program with Cuda or OpenCL. So this is going to be familiar to any C developer, Cuda, and it's a lot of C code pretty much. So it's not Java. So most computers you're going to buy today do have a GPU you can program to, and you can get the driver for free from NVIDIA's website. So why do we care? So here are the places where I see Java being used big time. So not just for big data projects. I can see you've got Spark on there, Hadoop, Hive, Cassandra. I put some sunglasses on Java because Java's fantastic. Down at the bottom, a few IBM products you guys don't really care for. Long story short, we have mainframes that run a lot of the world's important systems, and these are all running IBM Java. And in the press, you may have seen recently, there was AlphaGo, which beat the reigning champion, I think, for Go, and AlphaGo was a system using a lot of GPUs. So I think there's 176 GPUs in the final version, and you have a lot of CPUs. So these are great for processing lots of data at the same time, remember? And you can also see Titan, which is the second best supercomputer at the moment. Again, lots of GPUs, lots of CPUs. You've got CERN, I think I heard the conference actually. So I had a look, and they're using GPUs for something called Giant. Maybe I've said that wrong. And Oak Ridge and IBM, I've got a new deal to put some GPUs in some supercomputers worth a few $100 million. So people are caring about GPUs and are investing in it. So our key terms, here's what you're going to need to know. You're going to need to know that this thing called a Cuda core, okay? So these Cuda cores are part of a GPU, and you're going to have loads and loads of Cuda cores. The more, the better. You're going to have a kernel, and that is actually a function we're going to run on the GPU. This is code. So you've got a kernel, which is code, and when you run that kernel, these Cuda cores are going to be activated and going to run all your code in parallel. You've got a grid. Now a grid, think of the grid as a cube of blocks which lay out the threads. So remember, you've got loads and loads of threads. How do we tell each thread what to do? We use something called a grid. I'm going to tell you about it in more detail soon. Threads, you should know already, threads in all computing do all of the work. And remember, these CUDA cores execute loads and loads of threads, and you arrange the threads in blocks. Recommended reading down here. You get a command called NVIDIA SMI. It tells you what's on your GPU, how many threads can run at once, how many CUDA cores, how much memory you have. And by the way, the amount of memory is not usually very big on a GPU. Let's say 12 gig, maybe 24 gig. It's not massive. Some recommended reading for there if you're really interested. And here's some information on the grid. Now we need to know about this grid, so take my word for it now. In a few slides, we're going to get back to this. So why is it important? Well, we've got all of these threads, and how do we say, I want this thread to work on this piece of data? So with CUDA, you've got a grid. So I've stolen that picture. At the bottom, conveniently cut off, I give credits to the picture, but I've basically stolen this. And this tells us you've got block dimensions, so how many threads can you run on a certain block? And there's grid dimensions, which is how many blocks we can have. These, I'm talking about dimensions because these are actual attributes. So you might run a program and say, hey, how big can my grid be? How many threads can I run at once? So we can figure this all out with the Java API. And then you access things with variables like threadIDX.x. Just think of this as accessing an element in an array. So we might have a big, massive area of memory with loads and loads of data in, and we say, hey, threadIDX.x, the first time it's 0, and that might go up to 6 million. So this is going to be incrementing over time automatically for us. So that's the grid. I'm going to get back to this shortly. One thing I can do is tell you that the grid usually should be arranged like this. So you've got your problem size on the left. So that's how many elements you might have, maybe in an array. So we start off small with like 500 elements. You only want one block. Number of threads, 512 is typically fastest. You can profile this, and you can see that 512 is usually pretty good. So the bigger the problem, the more threads we're going to need. And here's how we actually program just in Cuda. So let's say you're just a C programmer and you really like using GPUs, you don't care for Java. Here's how you would do it. So we first have some data in memory. Let's just call it my data. Then you're going to allocate some space on the GPU with a Cuda malloc, and that tells you where that data's gone, so you get a pointer back. You can then use this pointer later on. And then you're going to copy your data from the host, or the CPU, over to the GPU. And then you're going to process your data in a kernel, we said that earlier, and you're going to copy the result back. And then, all done, head for my new favorite food, the ham and Cuda biota, and the manchego cheese, which is amazing. And thank you, Spain, for ham and Cuda biota. Hello, Malaga. This is like your first Cuda program. So it's going to look like this. So here's the actual code on the bottom. So here I've got an array of characters, and it's hello and a bunch of null characters. So at the moment, it's just rubbish. It's just hello. I mean, that's useless. What we're going to do is have 2 character star pointers here. So pointing to some chars. My device characters, that's what's going to live on the GPU. And then my device ints. So what we're going to do is transfer these integers to the GPU, and then we're going to apply these offsets to this. So we don't change the H, we don't change the E, L, L, or that O, but we do change this null character by 32. And in the end, after all of this, you get hello Malaga. And that executes in parallel. So we just do our mem copies down here, we call our kernel, and we get the result back. So we've got to do this every single time. Here's how that kernel actually looks. So you see this weird, so you've got 2 underscores here, and then global, and then 2 underscores again. So global means I can call this from the CPU. And then remember, this is going to be executed on a grid, and I've got threadIDX.x here to say, hey, this is going to be 0 the first time, and we launch a small grid. So I might only have, let's say, 16 threads. And it's going to go from 0 to, let's say, 16, and it's going to change them by the offset amounts. So here we go with Java. Now this is a complete pain. You don't want to code it this way. You've got to use a lot of JNI. So again, we've got some data in the Java heap. We're going to create a native method and then call this. You've got to then write some C code to the JNI, which basically does get elements. Then you've got to call the GPU. Then you've got to release the elements. And no one wants to do any of this. This is horrible. So over here, top right, you've got the Jenkins picture. So don't do it this way. So we're here to help, and this is our partnership with NVIDIA pretty much. So they're going to be including NVIDIA cards in a bunch of our power boxes, but don't worry about that for now. So the class library, this is our very first experiment. So this is easy peasy. Here's what you can do automatically. So there's that system property at the top, minus D IBM. So if I say enable, here's what will happen. So you come in, you want to sort some numbers, and we're going to go through this little flow chart on the left. So the GPU is really good if you've got a lot of data. If it's not much data, you've got to transfer it across, and that takes time, it ain't worth it. So we say, hey, is the problem size big enough? Okay, yeah, it is. Do you have a GPU available? Yeah, I do. And then, is the device capable? It might be a really naff graphics card. So if you say yes, sort on the GPU, get your result back. If it's not capable, do it on the CPU. If there's no GPUs, CPU. If it's too small, again, CPU. So you get your sorting throughput on the right, which tells you. So you got this line here is how many integers we can sort per second on a GPU. So about 400 million per second, and on the CPU down here, not much at all. So big difference, and here's how you use it. You write some normal Java code, set this property on the command line, and you're good to go. So who knows what a JIT is already? A few people maybe? JIT? Okay, nobody. Right. So I think you can get still really shy, but I'm going to tell you anyway. So with the JIT, it's going to be taking our Java bytecode and making some really fast native code to run different architectures. So what we've done is we've improved this. So it can actually spot some code you've written and then send it to the GPU for you. And that's easy to set. It's just one JIT option. So when you run your Java program, you do -xmx for your heap size, let's say. You might add our JIT option, and you've got a GPU, send the code to the GPU for you. So here's a performance chart. This is on the left, this is the elapsed time for a Spark benchmark without the JIT. Okay, so we're talking, let's say, 180 seconds for a few of the runs. And then over here, where you have a JIT with IBM Java, this is on Z, it's only a few seconds from these benchmarks. So a JIT is really important. So if you want to try it for yourself, just add -x into your Java command line, and you won't use the JIT at all, and you'll see it's so slow because it's in interpreted mode. So if you add this little option at the top, then you write some Java code with a lambda. So here I'm just saying, right, I've got an array, let's say it's 1 million elements. So from 0 to the 1 millionth element, you use a lambda, which is this bit in the braces. And all I'm going to do here is just times it by 2. And then our JIT will run, it will see this code, send it to the GPU, and it'll be faster, typically. So obviously it depends on how good your GPU is and how good your CPU is. You can do the same for a Java, a random function down here, and all you're doing is just a regular Java lambda. Though one thing to mention is that if you're on Windows, you've got to set up a really big path. It's the same on Linux, to be honest, as well. You need a lot of environment variables set, and I'll mention them later on. So here's what we can get for performance. Bear in mind, I don't really know much about these benchmarks. They're all for matrix multiplication. I don't know if you're going to do much matrix multiplication in your life, but if you are doing matrix multiplication, typically one GPU is a lot faster than 160 CPU threads. So we're talking about, being, let's say, 70 times faster, 100 times faster. Generally, using a GPU is best if you can do a lot of the work at the same time. So here's our Java API called Cuda for J. I can show you the code for this. I can show you a few examples. So instead of writing those native methods, so you've got some Java code, you've got some JNI code, you don't want to do that. You can just stay in the Java world, which you know and love. And one thing to mention, there is an existing implementation called JCuda. That's more like an exactual binding for Cuda, whereas ours is a new API that's quite easy to use, I think. So you can actually use it all for free by doing this. So you write a kernel, so that's our GPU function, remember? We save it as a text file, we compile that with this option. So a fat bin, that's just a fat binary file. And then we write your Java code using this package, ibm.cuda. And then you're going to write your Java code and you load up something like this, like it's a fat bin. So that, I renamed that file afterwards and I called it Adam Doubler. And it's a fat bin. And we build it and we run it as normal. So I can show you the code here. So on my laptop, I'm going to go over here and show you Eclipse. I can actually show you all of the code for how this is done. If we get time, I'm going to go back to this at the end, because chances are I'm going to go over there and it won't work. So for now, take my word for it, if you've got a Java API, I can show you the code. So Apache Spark. So who went to Tim's talk yesterday, Apache Spark? Anybody? Okay, a few people, maybe a dozen. That's good. So what we've actually done is we've optimized Spark to use GPUs for us behind the scenes. So what is Spark good for? For those that don't know, it's a very active open source big data project running in Java. There's a Scala API, Python API, and an R API, as well as a Java API. It's good for things like this. So machine learning. So there are a few pre-canned algorithms for recommendation. So let's say you're Amazon, let's say you're Spotify, you want to make recommendations, or maybe Netflix. They've got alternating least squares implemented for you, and that will scale out on many machines trivially. So you write maybe 10 lines of Scala code. I can then add 10 machines that will run this code on all of them. So alternating least squares is good. We can look at results for these reasons. Netflix, movie recommendations, recommended purchase on Amazon. So you log into Amazon, okay, maybe you want to buy a motorbike. It'll say, not a motorbike, a regular bicycle. They sell regular bikes on Amazon? Okay, maybe a computer. It'll say, hey, I think you want to buy a computer. Maybe you want to buy this computer because your friends or these people all went down the same search history and ended up buying this computer. So we can use alternating least squares for that. We can suggest music, maybe on Spotify or YouTube. There's also clustering algorithms called k-means, which is where you basically have lots and lots of data and you can say, I want 5 clusters. And it will say, okay, this data belongs to this cluster. So you probably can't see it over here, but it basically looks at people's intelligence and athletic ability. And in the US, you might have things like you've got typical things like the jocks who play American football all the time. You've got the smart kids who don't really get involved in football. And you can cluster it and say, okay, you've got this group of people, this group of people. You might want to tailor your product selling to different types of people. So maybe you want to target the jocks that want to buy footballs all the time or football shirts. So you can do k-means clustering of Spark. And there's also this one at the bottom, which is logistic regression. So you probably can't see this, but at the very bottom right, but there is a, hold on, I can't find my laser. There's a graph over there. Okay, my laser's gone. There's a graph at the bottom right, which basically says, okay, you plot a graph with some given data points, and you've got a new data point. You can say whereabouts on the graph this data point is going to go. Now, with that, you can use it to make decisions. So you plot it on the graph and say, hey, actually, chances are it was below or above the line, and it might be a line that says a spam filter. So you've got a graph, and it's above the line, maybe it's spam. Below it, it's not spam. And all of this is done in Spark, and you can use it to create a model. Now that's where your CPU gets used, or your GPU. So what we've done, this is all open source. We've got an implementation on GitHub at this link. And we've taken a well-known benchmark, which is a Netflix benchmark. It's not much data, to be honest, 1.5 gig. But we've shown that versus Intel hardware, we're around, let's say, 4 times faster when we just use 1 GPU. So this will, okay, I'll say 1. I actually mean 2 at the bottom. There's an Intel setup here. So you've got Intel setup, and you've got the GPUs at the bottom. And we found that using GPUs is around 4 times faster. And how do I do all of that? I just set one Java property, which is Spark mlib als.use GPU, and you get a performance increase. So we want to optimize these algorithms to use GPUs for you. We want to make it really easy to use. So I'm going to actually go over here. It's not a conclusion yet, so don't go for lunch just yet. It's free stuff if you've got a GPU. You can use hardware accelerator that you've got available. So let's say you've just gone and bought a new PC, you've got a GPU, you use it for video games. Now I'm going to write some, my program, my dissertation, my thesis. Use a GPU, get a performance benefit. Here's what we have and where it's available so far. Those 2 links at the bottom are where you can go and download this, all for free. And now I'm going to risk it and go over here and show you the Java code, okay? So bear with me. Okay, so now I'm in Eclipse, and you can all see that, which is good. I'm going to show you how easy it is to actually write some Java code. I've also got a make file where I can build this and run an example. So here I've got the com.ibm.cuda API. I've got 100 elements, and all I want to do is double these elements, okay, really, really easy. I'm going to fill the array first. I'm going to make a grid. I call that function that I was showing you earlier, where it says how big your grid should be, with this util.makeGrid command. And that tells me how big my grid's going to be. And I will say, okay, fine, I want some data from the GPU now. So I do buffer1 is new Cuda buffer. And I say which device to run it on. I want the first one. And then you say how big you want your buffer to be. So maybe it's 100 elements, it'll be 100 times by how big an integer is, because you've got 100 integers. Next step is to copy the data. So we just have one command called copy from. You're going from the CPU to the GPU. And then you set up your little kernel. So your kernel here has only got 2 parameters. So it's going to be the data to use, which is buffer 1, and then how many elements you want to do this function on. Then we launch it, and then this is for checking the result. We don't actually need these 2 lines of code. We don't need these 2. We copy it back, and you're done. You can check the results as well with a simple function. So I can run this, and I can break it if I wanted to, as follows. Right, so you can also, can you really see that? Okay, I'm going to show you the kernel, and I'm going to break it. So here we've got the doubler. That's a lot of comments. So there's my little kernel at the bottom, so it's not a lot of code, and all it does is say, hey, for the current element you're working on, take it and times it by 2. So if I make this times it by 3, right, and then I save that, I go back to my command prompt, and I run my scripts. The more my script does is calls that fatbin command, which builds the kernel, and then it says which version of Java you're on, compiles your program, and runs it. So here we can see how many incorrect results we have. Maybe you can't see it at the bottom, but it says 6. It says a lot of numbers down here, so a lot of incorrect results, incorrect results, incorrect results. So for the first problem, the smaller problem, it was only 100 elements. And I've got 3 test cases for bigger number of elements each time. So here it's saying 99 out of 100 are wrong. So 0 times 3 so gives me 0. So we're not all wrong. So now I'm going to go back to the kernel. I'm going to fix it. So I put a 2 in here. I save it, pressing Control S. I go back to my command prompt, and then I terminate that batch job. I run my command again, build it, and with any luck, we're going to see 0 incorrect results. There we go. So we do see 0. So I'm not sure if you can see that, but we've got no incorrect results. So I can then say, okay, that's fine for not many elements, but I've got 100 million numbers, and my GPU is not very good. I mean, maybe they won't fit on the GPU, maybe my grid size is restricted. So how do I chunk this data up? So I'm going to show you very quickly. I'm going to use one function for this, by the way, and here we go. So we've got 70 million elements. Now I know I can only execute a certain number of threads on the GPU at once. I'm going to chunk it all up in a while loop. So again, we fill it with integers, we create a new Cuda buffer, same as before, and we copy it to the GPU. And now we try to make a grid of this code, and it fails, so I get an exception. I know it's got an exception. And then I will say, fine, let's chunk it up. So down here, in the try-catch, we say, how big are your limits? How many threads can run at once? And you figure that out with these 2 calls here. Get attribute, so device max block dim and max grid dim. So if that's bigger than the amount of data you have, you got to split your problem up. And there's only one function to use for this. So I just do it in a while loop. I'm saying while you've still got numbers to double, you're going to do an if. And that if is saying if you're at the end of the doubling, instead of trying to double another, let's say 100 million, just do the remainder. So you chunk it up and then do the remainder at the end. And you will say, right, where have you got to so far? And you will use this slice API we have. And the slice one says, where do you want to cut from, and where do you want to cut to? And then each time you call your kernel, it'll operate on little bits of data at a time. So in theory, you've got a terabyte of data. Just keep chunking it up and send it to the GPU. And again, this will work for however much data you have in the first place. And so you've got your kernel over here. Remember, I've got add double a strider. And I load this in my Java code. I can make this anything that I want. And then over here in the Java world, I will send it to the GPU and be done. Now, there's only one thing to mention. There is a Lambda option to use. So I did mention this earlier, but I can turn this on and off quite easily. And if I just go back to our main demo, I'll show you what performance looks like. So I'm going to terminate this batch job. Now with my actual script, it runs a Lambda program. So while that builds and runs, I'm going to show you the Lambda one. And all the Lambda program does is some matrices multiplication. So you've got loads and loads of data, and we don't do anything complicated, we just matrix multiplication. We add the times the two together, and we say, did that take you long at all? And I'm just going to use one JIT option. So down here, that's done already. So that's, let's say, 2 seconds. And the CPU is still running in a Lambda, and it's going to take, let's say, 13 seconds. That's a guess. We won't be here all day. Okay, so that's done. Okay, that took 7.5 seconds. Now, all I did to make it go faster is to add one JIT option. I did mention it earlier, but here's my build it script. We just do this, -x JIT, enable GPU. If you put verbose on there, it tells you which GPU it used. That's pretty much it. So in conclusion, all of this is free. You can go and download it from DeveloperWorks. I'm not trying to, that's my flight information. I'm not trying to sell you anything. You can use our API, and this is all open source. Well, the Sparks is all open source. If you want to get involved, ambush me after this. My email is included in the presentation, so you can send me all your questions. And do we have any questions from the audience? No? Okay, if you're too shy, I'm going to linger around here and you can ambush me afterwards. So thank you for coming to this talk. Hope you enjoyed it. Adios. Hold on. Oh, wait. No! Got a question. No, stop clapping. You have a question. Hey, Ivan. Oh, yeah.
I missed the beginning of the talk, but did you talk at all about Apache and the way that that Apache is approaching offloading tasks to GPU?
So we had a question from Ivan about Apache. So as I understand it, Apache is an alternative way to use GPUs. I think it's for AMD cards, not NVIDIA ones. Not if I'm wrong. Okay, so Ivan's saying maybe. So we didn't actually look at Apache because we focused on NVIDIA cards for now. We can look into Apache or OpenCL, and this is all early days. If you want to use different cards, if there's demand for that, we'd be happy to look into it. So we think that our API is more Java-like than any other API. But having said that, I've not really been through Apache in detail. Any other questions for me? Okay, thank you very much. Adios.